There are places on this planet where definitions begin to soften, where what we call solid and what we call liquid enter into a conversation so slow and patient that it outlasts civilizations, where the boundary we imagine between stone and salt water reveals itself not as a line but as a long, quiet gradient stretching across both time and distance. You are looking for one of those places now, somewhere far from the noise of the surface, where the earth does not end and the ocean does not begin, but where both continue into each other, with a kind of geological tenderness that asks nothing of us except that we slow down enough to notice it. The night air is still, carrying only the faint salt of distant water and the coolness of rock that has not seen daylight in epochs, and if you listen carefully, you can almost sense the invisible meeting happening beneath you. Not dramatic, not sudden, just endlessly present. A transformation so gradual that no single moment contains it, but every moment participates in it. If this kind of quiet reflection helps you unwind, you can subscribe to Quiet Science and continue this journey with us. A place designed not for answers, but for the space between them, where understanding arrives slowly, like sediment settling through darkness. What does it mean for two elements to occupy the same space without conflict? For the planet's skin to be neither entirely one thing nor another, but some third condition we have no simple name for? A threshold that extends for miles in every direction and yet exists nowhere we can point to and say, here, this is where it happens. The ocean floor is not a floor at all, and the crust beneath it is not a ceiling, and between them lies something neither geography nor chemistry has fully captured, a zone of exchange so persistent and so unhurried that it rewrites both participants across millions of years, asking only that we set aside our need for edges and accept instead the reality of gradual becoming, the truth that nothing on this planet is ever truly separate, only moving at different speeds toward the same slow equilibrium. The boundary between Earth and ocean exists under a pressure so immense that it would collapse most of what we consider solid, a weight measured not in atmospheres, but in miles of water stacked vertically above the seafloor, each layer adding its patient contribution to the total burden. And yet this is not experienced as violence, but as a kind of slow certainty, the same certainty with which gravity holds the moon or time transforms mountains into sand. Down there, in the deepest trenches, and across the vast abyssal plains, the ocean presses against the planet's surface with a force equivalent to thousands of pounds concentrated on every square inch of rock. And the rock does not resist this pressure so much as accommodate it, allowing water to seep into its fractures and pores, permitting chemistry to occur at speeds we would call impossibly slow if we were forced to watch them happen, but which from the perspective of geology represent something closer to normal conversation than to silence. This is a place defined by waiting, where processes unfold across timescales that make human observation essentially meaningless, where the significant events are not explosions or earthquakes, but the gradual dissolution of minerals, the slow precipitation of new compounds from seawater, saturated with elements carried up from hydrothermal vents or down from the continents in river sediment, the patient accumulation of clay and calcite and silica that eventually becomes stone itself, indistinguishable from the basement rock it rests upon except in the details of its crystalline structure, the record of its formation written in layers thinner than paper but representing millennia each. The ocean floor is not static, though it appears so to any instrument we can deploy, moving instead with the unhurried certainty of tectonic plates drifting apart or converging, spreading at mid-ocean ridges where new crust forms from cooling magma, subducting at trenches where old crust returns to the mantle, and throughout this entire cycle, throughout every phase of the seafloor's long journey from birth to reabsorption, water is present, not as observer, but as participant, shaping and being, shaped by the rock it touches. Consider the simple fact that oceanic crust, the basaltic rock that forms the seafloor, contains more water than you might expect, not liquid water moving freely through it, but water bound chemically into the mineral structure itself, hydroxyl groups incorporated into the crystal lattices of serpentine and other altered minerals, water that entered the rock when it was still young and hot, when seawater circulated through its fractures and transformed olivine into something new, something more. Hydrated, something that carries the ocean's signature into the planet's interior when subduction eventually pulls it down. This is not contamination, but conversation. A chemical dialogue between elements that could not be more different in origin or character. One born from stellar nucleosynthesis and planetary differentiation, the other condensed from steam in the planet's early atmosphere. And yet here they are, millions of years into their relationship, inseparable. Not because they have merged into uniform substance, but because they have learned to coexist in the same space, each transforming the other in ways that accumulate slowly but irreversibly over time. The weight of the ocean above creates not just pressure, but possibility, enabling reactions that would not occur at the surface, allowing water to remain liquid at temperatures well above its normal boiling point, permitting minerals to dissolve and reprecipitate in configurations that reflect the unique conditions of the deep seafloor, the specific combination of pressure, temperature, and chemical composition found nowhere else on Earth, or perhaps anywhere in the solar system. These are not extreme conditions in the sense of hostile or inhospitable, merely specific, finely tuned by the physics of depth and the chemistry of seawater. And within these conditions, an entire architecture of interaction has developed, not designed by any intelligence, but emerging naturally from the properties of rock and water when given enough time and enough pressure to work with, enough darkness to proceed without interruption, enough stability to allow patterns to establish themselves across geological epochs. And what we discover, when we finally send instruments down to measure and cameras down to observe, is that this boundary we imagined as sharp and clear, this division between the planet's solid surface and its liquid envelope, does not exist in the form we expected. Instead, we find gradation, transition, a zone that extends vertically through hundreds of meters of sediment and fractured rock, horizontally across entire ocean basins, temporally across millions of years, a boundary that is less like a wall and more like a gradient in fog, visible from a distance, but impossible to locate precisely when you try to step through it, always receding, always present, never quite where you thought it would be. Perhaps this is what the planet has been trying to show us all along, that the categories we use to organize our experience of the world are useful but not ultimate, that beneath our need for clear distinctions lies a reality more interested in continuity than separation, more committed to gradual transformation than to permanent identity, a reality that does not recognize the difference between ocean and earth as anything more than a difference in phase, in density, in the arrangement of the same fundamental elements cycling through different states at different speeds, but always cycling, always moving, always becoming something slightly other than what they were, without ever ceasing to be themselves. There is a question that emerges naturally from this observation, one that does not demand an immediate answer, but instead invites patient consideration, and it concerns the nature of interaction itself, the possibility that two substances as fundamentally different as rock and water might occupy the same space not through competition or conquest, but through something closer to accommodation, a mutual adjustment that happens so slowly and so quietly that we might miss it entirely if we insist on looking for drama or conclusion. What does it mean for basalt, formed from molten rock erupted at temperatures exceeding 1,000 degrees, to encounter seawater at barely above freezing, and for this meeting not to result in catastrophe, but in transformation, a gradual exchange of properties that leaves neither substance unchanged, but both substances still recognizably themselves, still participating in their respective cycles, still contributing to the larger systems they belong to. The chemistry of this encounter is surprisingly gentle despite the extremity of the conditions involved, with seawater carrying dissolved ions of sodium, magnesium, calcium, chloride, and sulfate, among others, while the rock contains silica, iron, aluminum, and various other elements locked into crystalline structures formed under the immense pressures and temperatures of the upper mantle. When these two meet, when cold seawater enters the still warm fractures of newly formed oceanic crust, reactions begin that will continue for millions of years. Reactions that involve not the violent destruction of one substance by another, but the patient rearrangement of chemical bonds, the substitution of one ion for another in mineral structures that can accommodate this kind of change without collapsing, the formation of entirely new minerals that represent neither pure rock nor pure water, but something intermediate, something that could only exist at this boundary, under these specific conditions, given this much time. Scientists who study these processes use terms like hydrothermal alteration and serpentinization, words that describe in technical language what is essentially a conversation conducted in the vocabulary of chemistry, a slow negotiation in which water gives up some of its dissolved minerals and the rock gives up some of its structural integrity, and both participants end up different from how they began, more complex, more saturated with the history of their interaction. Serpentinization, for instance, occurs when water reacts with olivine and pyroxene, common minerals in the oceanic crust and upper mantle, transforming them into serpentine minerals that contain hydroxyl groups, those chemical fingerprints of water's presence, and in the process releasing heat and hydrogen gas, creating conditions that can support microbial life in the complete absence of sunlight, ecosystems that derive their energy not from photosynthesis, but from the chemical potential stored in rock, liberated gradually through its interaction with seawater. This is not a one-way process, not the ocean wearing away the rock or the rock contaminating the ocean, but a true exchange, with water entering the rock's interior through networks of fractures and pores, sometimes penetrating several kilometers into the oceanic crust, circulating through it like blood through tissue, carrying heat away from the rock and minerals into the ocean, then returning changed, warmer, enriched with elements that will eventually precipitate out in different locations, forming chimneys of metal sulfides around hydrothermal vents or accumulating as metalliferous sediments on the seafloor. The rock, meanwhile, cools and contracts, developing new fractures that allow even more water to enter, extending the zone of interaction deeper into the crust, transforming fresh basalt into altered basalt into fully hydrated serpentinite, each stage representing not decay, but evolution, the rock becoming more oceanic even as it remains fundamentally part of Earth's crust, carrying waterbound minerals that will eventually, when this piece of seafloor is subducted at a trench, be carried deep into the mantle, delivering the ocean's chemical signature into the planet's interior. What makes this interaction particularly remarkable is its patience, the way it unfolds across timescales that dwarf human civilization, with the most significant changes occurring not in minutes or days, but in millennia and millions of years. The rock gradually drinking the ocean gradually dissolving the rock, both processes happening simultaneously. Neither one dominating, neither one complete. Just this ongoing exchange that has characterized the seafloor since the first oceans, condensed and the first oceanic crust formed. An exchange so fundamental to the planet's operation that without it, Earth would be a different world. Perhaps one with a thicker crust and less volcanic activity. Perhaps one with different ocean chemistry and different conditions for life. Certainly, one with less connection between its surface and interior. Less communication between the domains we artificially separate in our minds. The mystery, if we can call it that, lies not in understanding the individual reactions, which chemistry can describe with considerable precision, but in comprehending the totality of the system, the way these countless small exchanges add up to something larger than their sum, the way the boundary between rock and water becomes not a barrier, but a membrane, not a place where one thing stops and another begins, but a zone of active negotiation where both things continue into each other, where the distinction between them becomes less about composition and more about rate of change, about which molecules are currently bound into solid structures and which are currently dissolved in liquid, with the understanding that these roles are temporary, that everything is moving, everything is cycling, everything is slowly becoming something else while remaining essentially itself. And perhaps this is the deeper lesson available here, beneath the chemistry and the geology, something about the nature of boundaries themselves, the way they exist not to separate, but to mediate, not to define edges, but to facilitate exchange, not to preserve pure categories, but to enable the kind of gradual transformation that characterizes all complex systems over sufficient time, showing us that what we call distinct is often merely distinguishable, still connected, still conversing, still participating in relationships that transcend the definitions we place on them. The seafloor is born in darkness, miles below the surface, at places we call mid-ocean ridges, but which might be better understood as long wounds in the planet's skin, places where tectonic plates pull apart and magma rises from the mantle to fill the gap, not violently but steadily, continuously, at rates measured in centimeters per year, about as fast as your fingernails grow, which means that the process is simultaneously always happening and never visible. Too slow to watch, but too constant. To stop, a planetary heartbeat that has been pulsing since plate tectonics began, and will continue until the Earth's interior cools enough to solidify completely, an event so far in the future that it exists only as theoretical calculation, not as anything we need to concern ourselves with tonight. When this molten rock, this basaltic magma carrying heat from the upper mantle, encounters the near-freezing seawater of the deep ocean, something remarkable happens, a transformation that occurs in seconds, but whose consequences unfold across millions of years. The outer surface of the lava cools almost instantly, forming a glassy rind that seals in the heat beneath. But the pressure of more magma rising from below eventually cracks this rind, allowing molten rock to bulge out like toothpaste from a tube, forming rounded masses that geologists call pillow lavas because of their shape, though they are hard as any rock and considerably heavier than any pillow you have rested your head upon. These pillows stack atop each other, layer upon layer, building the foundation of new oceanic crust, and between them seawater circulates, penetrating into the still warm rock, beginning that conversation we spoke of earlier, starting the long process of chemical exchange that will define this piece of seafloor for the rest of its existence. The temperature difference is extreme, more than 1,000 degrees Celsius separating the molten interior from the surrounding water, and yet the water does not boil away into steam, prevented from doing so by the immense pressure of the ocean above, which keeps it liquid even at temperatures that would vaporize it instantly at the surface. Instead, the water near the rock becomes superheated, rising through the fractured crust in convection currents, carrying dissolved minerals leached from the surrounding rock, while cold seawater sinks down to replace it, establishing circulation patterns that can extend several kilometers into the newly formed crust, heating and cooling, dissolving and precipitating, transforming fresh basalt into something more complex, more hydrated, more oceanic in character, all within the first few million years of its formation, which in geological terms represents infancy, the earliest stage of a journey that will eventually carry this rock across an entire ocean basin and possibly into a subduction zone where it will be recycled back into the mantle. This creation happens along a system of ridges that spans more than 40,000 miles around the planet, longer than the circumference of the Earth at the equator, a continuous network of volcanism operating beneath the ocean's surface, hidden from direct observation for most of human history, unknown until the mid-20th century, when echo sounding and other technologies finally revealed the ocean floor's true topography. The ridges rise several thousand meters above the surrounding abyssal plains, not because the crust is thicker there, but because it is hotter, less dense, more buoyant, floating higher on the underlying mantle. And as this new crust moves away from the ridge on its tectonic plate, it cools and contracts, subsiding gradually, sinking deeper into the mantle as it ages, creating the characteristic profile of the ocean floor, high at the ridges, deepening with distance, oldest and deepest at the trenches where subduction eventually claims it. What we are witnessing, when we observe these processes, is planetary renewal, the mechanism by which Earth recycles its surface, preventing the permanent buildup of continents, maintaining the balance between creation and destruction that characterizes active planets, worlds that have not yet cooled into geological death. Every year, approximately 20 square kilometers of new oceanic crust forms at ridges around the world, and an equivalent amount is subducted at trenches, keeping the total area of seafloor roughly constant, maintaining the ocean basins as stable features despite the constant motion of the plates that contain them. This is not equilibrium in the sense of nothing changing. but equilibrium in the sense of balanced flows, inputs matching outputs, creation matching destruction, and all of it happening so slowly that the ocean appears eternal. The seafloor appears permanent, when in fact both are engaged in constant transformation, constant cycling, neither one the same from one epoch to the next, even though both remain recognizably themselves. The rock that forms at these ridges carries within it a record of Earth's magnetic field at the moment of its creation, iron-bearing minerals aligning themselves with the planet's magnetic poles as they crystallize, then freezing that alignment into place as they cool below a certain temperature, creating stripes of normal and reversed polarity that parallel the ridge on both sides. Proof that the seafloor is indeed spreading, that the ridge is indeed creating new crust continuously, that the ocean floor is younger near the ridges and older farther away. A pattern so clear once you know to look for it that it seems obvious, though it took decades of careful measurement and theoretical work to recognize it, to understand what it meant, to accept that the seafloor is not ancient and unchanging but young and constantly renewing itself, born again with every surge of magma, every pillow of cooled lava, every circulation of heated seawater through fresh basalt. And so the boundary begins here, at these ridges, at this meeting of molten rock and frigid water, at this moment of transformation when the planet's interior becomes its surface, when heat becomes structure, when liquid becomes solid, not all at once but gradually, progressively, with the rock cooling from outside in, with water infiltrating from outside in, both processes working together to create something that is neither purely magma nor purely seawater, but a third thing, oceanic crust. Foundation of the ocean floor, temporary surface of the planet, destined to journey across a basin and then return to the mantle, completing a cycle that takes roughly 200 million years, which seems like forever, but which the planet has repeated many times already and will repeat many times more, as long as its interior remains hot enough to drive the motion of plates, to maintain this slow but constant renewal, this quiet but persistent conversation between rock and water that has shaped the Earth we inhabit. Once the new crust has formed and begun its slow journey away from the ridge, another process starts. Quieter still, almost imperceptible even to instruments designed to measure such things, and that is the gentle accumulation of sediment, particles falling through miles of water like snow through a winter sky, taking weeks or months to complete their descent, settling onto the bare rock with a softness that leaves no crater, no disturbance, just the patient addition of layer upon layer, micron upon micron, building a blanket that will eventually bury the volcanic landscape beneath a smooth plain of fine-grained material that looks nothing like the rock it covers, but which becomes, over time, inseparable from it, welded to it by pressure and chemical bonding, transforming from loose sediment into solid sedimentary rock through processes that require millions of years and the weight of all the sediment that accumulates above. This sediment arrives from multiple sources, each contributing its own character to the mixture, with some particles originating as the shells and skeletons of microscopic organisms living in the sunlit surface waters, creatures called foraminifera and coccolithophores and radiolarians, names that sound exotic but which refer to some of the most abundant organisms on Earth, beings that extract dissolved calcium carbonate or silica from seawater and use it to build intricate structures that protect their soft bodies, structures that become, upon the organism's death, particles of sediment, sinking slowly through the water column, accumulating on the seafloor as ooze, a term that sounds unpleasant, but which describes something rather beautiful, a soft white or tan or grey deposit made entirely of the remains of countless tiny lives, each one having participated briefly in the surface ocean's light and warmth before contributing its body to the growing thickness of sediment below. Other particles arrive from the continents, carried by rivers and wind, dust and clay eroded from mountains and plains, and transported across thousands of miles to settle finally on the deep ocean floor, far from their origin, mixed now with the biological debris, adding minerals and elements that were never part of any living organism, quartz grains worn smooth by their journey, clay particles so fine they remain suspended in seawater for years before finally settling, all of it contributing to the heterogeneous mixture that becomes pelagic sediment, sediment of the open ocean, distinct from the coarser sediments found near continental margins, finer, purer, more uniform in its slow accumulation, recording in its composition the history of the ocean above and the continents beyond. A library written in particles too small to read without magnification, but which together tell stories spanning millions of years. The rate of accumulation varies depending on location and on the productivity of the overlying water, with some areas receiving several centimeters of sediment per 1,000 years, while others receive only millimeters. Differences that seem trivial until multiplied across geological time, until you realize that even at the slower rate, you will build hundreds of meters of sediment over the lifespan of a typical piece of oceanic crust, enough to completely bury the original volcanic topography, enough to transform a rough landscape of pillow lavas and volcanic ridges into a flat, abyssal plain, smooth as a frozen lake, revealing nothing of the complex geology beneath, hiding it under a blanket that is itself complex, layered, containing within it the record of changing ocean conditions, shifting current patterns, variations in biological productivity, all preserved in subtle changes in sediment composition and grain size that require careful analysis to detect, but which are there, waiting to be read by anyone patient enough to extract a core and study it carefully. But sediment is not inert, not simply accumulating passively, because even as it settles, it participates in chemical exchanges with the seawater that permeates it, with pore water filling the spaces between particles, carrying dissolved ions, facilitating reactions that alter both the sediment and the water, precipitating minerals, dissolving others, establishing chemical gradients that drive diffusion and movement, even in the absence of any visible current or flow. Calcium carbonate, for instance, dissolves more readily under the high pressure and low temperature of the deep ocean, particularly below a depth called the carbonate compensation depth, usually found around 4 or 5 kilometers below the surface, below which carbonate sediments cannot accumulate because they dissolve faster than they arrive, meaning that the deepest parts of the ocean are covered not with white calcareous ooze, but with red or brown clay, sediment that contains no carbonate at all, only the residue of what cannot dissolve, the most resistant minerals accumulating at rates so slow that a single centimeter might represent 10,000 years, a thickness you could cover with your fingernail representing more time than all of recorded human history. Within this sediment, within the pore water between particles, minerals precipitate slowly from solution, manganese nodules growing at rates of millimeters per million years, potato-sized lumps of metal oxides that form directly on the seafloor or just beneath it, concentrating elements like manganese, iron, cobalt, and nickel that are dissolved in seawater at concentrations far too low to precipitate normally, but which accumulate gradually around some nucleus, some shark tooth or rock fragment. That provides a starting point, a seed crystal that grows imperceptibly, atom by atom, layer upon layer, so slowly that they have become symbols of geological patience, examples we cite when we want to communicate what it means for something to happen at Earth's pace rather than at ours. Reminders that the ocean floor is not finished, not complete, but constantly adding to itself, constantly transforming, constantly blurring the distinction between what is rock and what is sediment and what is water, showing us that these categories exist more in our need for classification than in the actual substance of the seafloor, which recognizes no such boundaries, only gradations, only transitions, only the slow exchange of material between phases, between states, between identities that are never fixed, but always flowing, always becoming, always participating in transformations too gradual to witness directly but too fundamental to ignore once you understand that they are happening, that they have always been happening, that the boundary we are trying to understand is not a place, but a process, not a line, but a zone, not a division, but a conversation that has continued without interruption since the first oceans formed and the first seafloor cooled and the first particles began their long, slow fall through darkness toward the bottom. Beneath the sediment, beneath the quiet accumulation of particles, the rock itself remains active, not in any dramatic sense, but in the way that all things remain active when given enough time and the right conditions. And one of those conditions is heat, residual warmth from the rock's formation, or heat flowing upward from the mantle below, enough to drive circulation, to create movement in water that has penetrated deep into the fractured crust, water that becomes an agent of transformation. Once it is heated, once it begins to rise through the rock's natural pathways, carrying with it dissolved minerals leached from the surrounding basalt, becoming a solution so enriched with elements from Earth's interior that when it finally emerges back into the cold ocean, it will precipitate those minerals almost instantly, building structures that seem alien, chimneys and mounds and delicate formations that would not be out of place in science fiction, but which are entirely natural, entirely the result of simple physics and chemistry operating without supervision, without design, just following the logic of temperature gradients and mineral solubility and the patient architecture of the fractured seafloor. These hydrothermal systems, as we call them, operate on a cycle that can be thought of as the ocean breathing through the crust, inhaling cold water at one location and exhaling hot water at another, with the entire cycle taking anywhere from a few years to several decades, depending on the depth of circulation and the permeability of the rock. And during that time, the water is not passive, not merely being heated and cooled, but actively dissolving and transporting, stripping magnesium from the higher seawater and replacing it with calcium from the rock, removing sulfate and adding hydrogen sulfide, transforming the chemical composition of both the water and the rock it passes through, creating conditions so different from normal seawater that when this hydrothermal fluid finally emerges at a vent, it is essentially a different substance, acidic instead of alkaline, metal-rich instead of salt-dominated, hot enough to melt lead, but prevented from boiling by pressure, billowing upward through the surrounding cold seawater like smoke from an industrial chimney, black or white depending on the minerals it carries, visible proof of the constant exchange happening between the planet's interior and its ocean. The vents themselves are temporary features, lasting perhaps decades or centuries before the pathways that feed them become clogged with precipitated minerals, or the heat source beneath them shifts, or the tectonic forces that created the fractures in the first place rearrange the rock enough to redirect the flow elsewhere. But during their active lifetime, they represent one of the most concentrated interfaces between rock and water on the entire seafloor, places where the boundary is not diffuse but immediate, where hot, mineral-rich fluid meets cold, oxygenated seawater, and the result is precipitation so rapid you could watch it happen if you were there. Minerals coming out of solution as soon as the conditions change, building structures that grow centimeters per day, fantastically fast by geological standards, though still slow enough that you would need time-lapse photography to see the motion, still patient enough that the structures they build have texture and complexity, rather than the smooth uniformity of something formed quickly without variation. What emerges around these vents is chemistry in visible form, with iron sulfides creating the black smoke of what we call black smokers, while barium and calcium sulfates create the white smoke of white smokers, and the chimneys themselves become layered records of changing conditions, with different minerals precipitating at different temperatures, creating concentric zones that reflect the thermal gradient between the hot core and the cold exterior. Some minerals stable only above certain temperatures and others only below, so that, as the fluid cools during its passage through the chimney walls, it deposits different minerals in sequence, building structures that are not random but organized, not chaotic but patterned, showing us that even without conscious direction, the world tends toward order. When given enough constraints and enough time, that structure emerges naturally from repeated processes, that form follows function even in chemistry, even in the interaction between hot water and cold sea and the minerals dissolved between them. But the vents are only the most visible part of a much larger system, only the exhale in the breathing cycle, And for every plume of hot water rising from a vent, there are vast areas of seafloor quietly drawing cold water downward, diffuse flow happening across wide areas rather than concentrated in chimneys, water seeping into the rock through countless small fractures, beginning its journey into the crust where it will be heated and altered, before eventually rising somewhere else, perhaps at a vent, perhaps through more diffuse seepage, completing a circuit that connects the ocean's bottom to the rock's interior in a continuous loop, a circulation pattern that has existed as long as there have been oceans and oceanic crust, that will continue as long as the Earth's interior remains warm enough to drive it, that represents one of the fundamental ways the planet manages its heat, one of the mechanisms by which energy from the core and mantle reaches the surface and is transferred to the ocean and ultimately radiated into space, maintaining the thermal balance that keeps Earth's interior molten and its surface temperate, that prevents the planet from either overheating or freezing, that maintains conditions suitable for the existence of liquid water in the first place. The total amount of water cycling through oceanic crust this way is staggering when you calculate it, with estimates suggesting that the entire volume of the world's oceans passes through hydrothermal systems roughly every 100,000 to several 100,000 years, which means that over geological time, every drop of seawater has likely passed through oceanic crust multiple times, has been heated and altered, has participated in the chemical exchange between rock and ocean, has carried minerals from inside the planet to its surface, has contributed to the ongoing conversation between solid and liquid that defines this boundary we are exploring. The ocean you see from shore is not separate from the rock beneath it, but intimately connected, constantly exchanging material, constantly adjusting its composition based on interactions with the seafloor, deriving much of its dissolved mineral content not from rivers alone, but from this deeper source, this direct connection to Earth's interior, this hydrothermal pathway that brings elements like iron, manganese, zinc, copper, and many others into solution where they can be used by organisms, or precipitated as sediment, or simply remain dissolved, contributing to the ocean's overall chemistry, its characteristic saltiness, its particular combination of elements in specific ratios that reflect the cumulative result of billions of years of rock-water interaction, of weathering and erosion and dissolution and precipitation, all operating simultaneously, all contributing to the chemical signature of seawater, that complex solution that is neither purely the result of evaporated rain, nor purely the result of dissolved rock, but something intermediate, something that could only exist at the interface between water and stone, that embodies the boundary we are trying to understand, that demonstrates through its very composition the impossibility of truly separating ocean from earth. Pressure, when you consider it carefully, is not merely weight from above, but a kind of intimacy, a forcing together of things that might otherwise remain separate, molecules compressed until their electron clouds overlap, atoms pushed so close that their normal behaviors change, reactions that would never occur at the surface, becoming not just possible, but inevitable, once you descend far enough into the ocean, once the miles of water above exert their collective influence on everything below. At the seafloor, several kilometers down, pressure reaches levels measured in hundreds of atmospheres, hundreds of times the pressure we experience at sea level, enough to compress water itself, making it slightly denser than it would be at the surface, enough to allow that water to remain liquid at temperatures that would vaporize it instantly if you brought it upward, enough to enable chemistry that operates by different rules, following the same fundamental principles but expressing them in ways that seem strange until you understand that pressure is not an obstacle but a participant, not something working against reactions, but something enabling them, opening pathways that altitude would close, maintaining conditions that elevation would destroy. This pressure works its way into the rock, not directly, but through the water that permeates it. And water under pressure behaves differently than water at the surface, more aggressive as a solvent, more capable of penetrating small spaces, more effective at breaking chemical bonds and facilitating new ones, carrying this enhanced reactivity deep into the fractured oceanic crust, several kilometers down in some places, far below the seafloor, far from any light or any obvious sign that the ocean extends this deep, and yet the water is there, trapped in pore spaces and moving slowly through fracture networks, migrating downward and laterally and eventually upward as it is heated from below, as it becomes part of hydrothermal circulation. But even water that does not circulate, even water that remains relatively static within the rock, participates in transformation, altering the minerals it contacts, being altered in turn, establishing a chemical equilibrium that reflects the specific conditions of temperature and pressure at that depth, at that distance from the seafloor, at that stage in the crust's evolution. The minerals that form under these conditions are different from those that crystallize directly from magma, different from those that precipitate at the surface, representing instead a third category that geologists call metamorphic, meaning changed in form, minerals that have been transformed by heat and pressure without melting, without returning to liquid state, maintaining their solid structure while rearranging their internal architecture, substituting one element for another, incorporating water into crystal lattices that were originally anhydrous, creating new minerals with new properties, new colors, new densities, new stabilities, each one reflecting the particular combination of conditions that created it. Serpentine forms from olivine when water is present, chlorite from pyroxene, actinolite from plagioclase, a whole suite of hydrated minerals that could not exist without water's participation, without pressure keeping that water in contact with the rock long enough for reactions to proceed to completion, without temperature providing the activation energy necessary to break old bonds and form new ones. These transformations happen progressively in zones that correspond to depth and therefore to temperature, with the lowest temperature minerals forming nearest the seafloor, where circulating water is coolest, higher temperature minerals forming deeper, where the rock is warmer, and the highest temperature phases forming at the base of the hydrothermal system, where water approaches the hottest rock, creating a vertical stratification that mirrors the thermal gradient, each zone containing minerals stable only within a certain temperature range, minerals that record in their composition and structure the conditions of their formation, the specific point in the rock's cooling history when they crystallized, the particular chemistry of the water that was present at that moment. Geologists can read this layering like tree rings, reconstructing from a sample of altered oceanic crust the entire history of its interaction with seawater, the depth of water penetration, the maximum temperatures reached, the duration of hydrothermal activity, all encoded in the mineralogy, in the subtle variations in composition and texture that careful analysis can reveal. But what is most remarkable about this transformation is not its completeness, but its gradualness, the way it happens incrementally, with fresh basalt at the center, grading through increasingly altered zones toward completely metamorphosed rock at the periphery. No sharp boundaries, no sudden transitions, just continuous gradation across space and time, showing us that the rock does not switch from one state to another, but flows through a spectrum of states, each one slightly different from the last, each one representing equilibrium with conditions that are themselves changing as the rock ages and cools and moves away from the ridge, as new fractures form and old ones seal, as water continues to circulate or stops circulating or changes its pathway, responding to shifts in permeability and pressure and thermal structure that the rock's own alteration creates. Because as minerals change, they also change the rock's properties, making it more or less permeable, more or less dense, more or less reactive, setting up feedback loops where alteration enables further alteration, where the rock's interaction with water changes the rock in ways that affect how it interacts with water, creating complexity that increases over time, rather than decreasing, diversification rather than uniformity, heterogeneity rather than homogeneity. The result, after millions of years, after this piece of oceanic crust has traveled halfway across an ocean basin, cooled from hundreds of degrees to barely above freezing, accumulated hundreds of meters of sediment on its surface, is something that bears little resemblance to the fresh basalt that erupted at the ridge. Though it is made of the same elements, still fundamentally igneous rock in origin, still part of the oceanic crust, still serving the same structural role in plate tectonics, just transformed, matured, saturated with history, carrying within its altered minerals the accumulated evidence of all its encounters with seawater, all the chemical exchanges, all the temperature changes, all the slow adjustments to equilibrium that have characterized its journey so far. The boundary between rock and water we begin to see is not something that exists only at the surface, only where rock meets ocean in the most obvious sense, but extends downward through the entire thickness of permeable crust, wherever water can penetrate, wherever conditions allow reaction, wherever the timescale is long enough for chemistry to express itself fully, which in practice means almost everywhere. Almost the entire volume of oceanic crust participates in this boundary to some degree, carries some signature of water's presence, has been touched and altered and made more complex by its interaction with the ocean above, showing us that what we thought was a surface phenomenon is actually volumetric, that the interface extends in 3 dimensions and 1 dimension of time, that we cannot point to any single location and say here is where ocean ends and Earth begins, only that somewhere in this vast transitional zone, spread across kilometers vertically and thousands of kilometers horizontally and millions of years temporally, the two are meeting, mixing, becoming something neither one was originally, but both have contributed to making. Eventually, after its long journey across the ocean basin, after decades of cooling and alteration and sediment accumulation, the oceanic crust arrives at a trench, one of those places where 2 tectonic plates meet, and one begins to slide beneath the other, descending back into the mantle from which it originally came, completing a cycle that has taken perhaps 100 million years, perhaps 200, depending on the size of the ocean and the speed of plate motion, but always long enough that the crust entering the trench is fundamentally different from the crust that formed at the ridge, colder, denser, more hydrated, weighted down with sediment, ready in a sense to sink, to return to depth, to carry everything it has accumulated during its time at the surface back into the planet's interior, including the water it has absorbed, the water bound chemically into its altered minerals, the water trapped in pore spaces between sediment grains, all of it going down, not lost, but redistributed, not destroyed, but transformed yet again, participating in cycles within cycles, exchanges within exchanges, boundaries within boundaries. The trench itself is a remarkable feature, the deepest part of the ocean, deeper than mountains are tall, a groove in the seafloor where the descending plate bends downward, flexing under the strain of subduction, developing new fractures that allow yet more water to enter the crust, even as it begins its descent, even as it leaves the seafloor behind and starts moving into the mantle, carrying its cargo of seawater and sediment and altered rock into conditions of increasing temperature and pressure, conditions that will eventually drive that water back out, not all at once but gradually, progressively, as the increasing heat breaks down hydrated minerals and releases the water they contain, sending it upward through the overlying plate, creating new pathways for circulation, new opportunities for rock-water interaction, maintaining the boundary even here, even at depths where you would think the ocean could not possibly reach, where temperatures exceed anything water should be, able to withstand, and yet the water is there, or was there, or is in the process of leaving, depending on the depth and the specific mineral being considered, because different hydrated minerals are stable to different depths, releasing their water at different temperatures, creating a cascade of dehydration reactions as the slab descends, each one contributing water to the mantle wedge above, each one participating in the processes that generate magma and drive volcanism at the surface, connecting the deep trench to the volcanic arc that parallels it, showing us that subduction is not simply destruction, but transformation, not an ending, but a transition, not the cessation of the boundary, but its continuation in a different form, at a different location, under different conditions. Some of the water released from the descending slab rises into the overlying mantle wedge and lowers the melting point of the rock there, enabling magma to form at temperatures lower than would otherwise be required. Magma that rises toward the surface and eventually erupts at volcanoes that form a chain parallel to the trench, the volcanic arc that characterizes subduction zones, whether we are talking about the Andes, or the Japanese islands, or the Aleutians, or any of the other places where oceanic crust descends beneath continental or other oceanic crust, bringing water from the ocean floor into the mantle and then returning it to the surface as steam in volcanic eruptions, completing a circuit that connects the deep ocean to the atmosphere, the seafloor to mountaintops, the coldest and darkest places on Earth to some of the hottest and brightest, all linked by this water that cycles through the system, that refuses to stay in any one place or any one state, but keeps moving, keeps participating, keeps crossing boundaries and connecting domains that seem separate but which reveal themselves, when you trace the pathways carefully, to be parts of a single integrated system. But not all the water escapes. Not all the hydrated minerals break down even at the depths of subduction zones, with some fraction of the water being carried past the zone of dehydration, past the point where it could rise into the mantle wedge, continuing downward with the descending slab into the deep mantle, potentially all the way to the core mantle boundary, carrying the ocean's chemical signature into the planet's deepest interior, mixing it into mantle convection patterns that operate on timescales of hundreds of millions of years, that eventually bring material back to the surface at mid-ocean ridges or hotspots, completing cycles so long and so complex that we have only begun to understand them in the past few decades, only started to appreciate how interconnected the surface and interior really are, how much exchange occurs between them, how little of Earth's structure is truly isolated or independent, how the boundary between ocean and solid planet extends not just across the seafloor and through the upper crust but down into the mantle, possibly even deeper, creating a system of such scope and such complexity that it encompasses essentially the entire planet, from the atmosphere to the core, with water serving as the primary medium of connection, the substance that links these domains, that carries material and energy between them, that enables the kind of chemical and thermal exchange necessary for Earth to remain geologically active, for plate tectonics to continue operating, for the surface to remain habitable. The timescales involved in this deep water cycle dwarf even the already impressive timescales we have been discussing, with water subducted into the deep mantle, potentially remaining there for 1 billion years or more before returning to the surface, circulating through convection currents that move at speeds measured in centimeters per year, mixing and stirring and gradually homogenizing the mantle's composition, while also maintaining certain chemical heterogeneities that tell us the mantle is not a uniform substance, but a complex mixture of materials with different histories, different origins, different pathways through the planet's interior, some of which include visits to the surface, time spent as ocean or rock or atmosphere, before being recycled back down, participating in a planetary metabolism that processes and reprocesses the same material over and over, never creating anything truly new, but constantly rearranging what exists, constantly recombining elements, constantly discovering new equilibria that reflect current conditions rather than original configurations, showing us that Earth is not a finished object, but an ongoing process, not a static arrangement of materials, but a dynamic system, maintaining itself far from equilibrium through the constant exchange of energy and matter between its various reservoirs, of which the ocean is one and the mantle is another, and the crust is a third, all connected, all influencing each other, all participating in transformations that blur any clear distinction between them, that make it impossible to say where one truly ends and another begins, that force us to acknowledge the planet as fundamentally unified, fundamentally continuous, fundamentally impossible to divide into separate, independent parts without misunderstanding its essential nature. We are accustomed to thinking of the water cycle as something that happens in the air and on the surface. Evaporation from the ocean lifting moisture into the atmosphere, where it condenses into clouds and falls as rain, flowing through rivers back to the sea, a circuit that takes days or weeks or at most years to complete, visible and comprehensible, the kind of cycle you can watch happen if you pay attention to weather, to seasons, to the movement of storms across the sky. But this familiar cycle, this rapid exchange between ocean and atmosphere and land, represents only a fraction of the water moving through Earth's systems, only the fastest and most obvious loop in a much larger network of exchanges that includes pathways through solid rock, through the mantle, through regions so hot and so pressurized that water as we know it cannot exist. Yet water is there nonetheless, present not as liquid or vapor, but as hydroxyl groups bound into mineral structures, as hydrogen and oxygen atoms separated and incorporated into crystals, as components of rock that is technically solid, technically dry in any conventional sense, but which nevertheless contains water, holds it, transports it, releases it under the right conditions, participating in a slow water cycle that operates on geological time, that takes millions of years per circuit, that involves volumes of water comparable to or exceeding the entire volume of the surface oceans, hidden from view, invisible to any casual observation, known to us only through careful measurement and theoretical inference, through the patient work of scientists studying rock samples and seismic data and the chemistry of volcanic gases, piecing together evidence of a planetary water cycle that encompasses not just the surface, but the interior, not just the rapid exchanges we can see, but the slow exchanges we can only imagine. This deep water cycle begins, as we have seen, with hydration of oceanic crust, with seawater penetrating into the rock and becoming chemically bound into minerals, then continues with subduction, with that hydrated crust descending into the mantle and releasing its water at depth, some of it rising to generate arc volcanism, returning to the surface relatively quickly within a few million years, but some continuing down past the arc into the deeper mantle where it may remain for hundreds of millions of years, perhaps longer, mixing into mantle convection, spreading through vast volumes of rock, becoming so dispersed and so diluted that it is no longer identifiable as water from any particular ocean or any particular episode of subduction, but simply as hydrogen and oxygen that happen to be present in the mantle's mineral assemblage, part of the background composition, part of what makes Earth's mantle different from the mantles of other rocky planets that lack plate tectonics, that lack the mechanism for cycling surface water into the interior, that may have had oceans once, but lost them to space because there was no way to store water in their interiors, no reservoir that could protect it from ultraviolet radiation and solar wind, no deep cycle that could maintain a balance between surface and interior over billions of years. The mantle holds, according to current estimates, at least one ocean's worth of water, and possibly several, not as liquid obviously, but as hydroxyl incorporated into minerals like wadsleyite and ringwoodite that exist only at the high pressures of the transition zone, a region several hundred kilometers below the surface where the mantle's olivine transforms into denser crystal structures that can accommodate more water in their lattices, that serve as a kind of reservoir, a holding area where water can accumulate or from which it can be released depending on temperature and pressure conditions, depending on the movement of mantle convection, depending on whether material is rising toward lower pressures, where hydrated minerals become unstable and release their water, or sinking toward higher pressures, where water can be absorbed again, creating a complex vertical circulation of water within the mantle itself, separate from the surface ocean but connected to it through subduction and volcanism, through the slow but persistent exchange at plate boundaries, through the fact that what goes down must eventually come up, though not necessarily in the same form, not necessarily through the same pathway, not necessarily within any time frame we would recognize as return, just eventually, given enough time, given the relentless stirring of mantle convection, given the fact that the mantle is not static but mobile, not frozen but slowly flowing, carrying everything within it through. Circuits that span the planet's interior, that bring material from the surface to the core mantle boundary and back over hundreds of millions of years, mixing and homogenizing, but never completely, always maintaining some heterogeneity, some chemical signature of different sources and different histories, some trace of the surface water that was subducted, and the volcanic water that was erupted, and the original water that was present when the planet formed, all of it circulating together, all of it contributing to the mantle's overall composition, all of it participating in a cycle so vast and so slow that it makes the surface water cycle seem instantaneous by comparison, makes the ocean seem like a shallow film on the planet's surface rather than the dominant reservoir we imagine it to be. And yet the surface ocean is not unimportant, not merely a minor component of the total water budget, because it is through the surface ocean that exchanges with the atmosphere occur, that life exists, that rapid recycling happens, that conditions vary enough to create the diversity of environments and chemical regimes necessary for complexity to emerge, for evolution to proceed, for intelligence to develop, for consciousness to arise and begin asking questions about boundaries and cycles and the nature of the planet it inhabits. The surface ocean, despite containing only a fraction of Earth's total water, plays a role disproportionate to its volume, because it is at the interface, at the boundary between atmosphere and solid Earth, participating in both realms, affected by both, mediating between them, moderating temperature extremes, distributing heat from equator to poles, absorbing carbon dioxide and releasing oxygen, hosting ecosystems that produce most of the planet's oxygen and fix most of its carbon, serving as both a physical and chemical buffer that maintains conditions within the narrow range necessary for life as we know it, and doing all this while also participating in the deep cycle, while also exchanging with the interior, while also feeding water into subduction zones and receiving it back from volcanoes, connecting the surface to the depths in ways that ensure neither can be understood in isolation, that force us to see the ocean and the solid Earth not as separate entities, but as aspects of a single integrated system, phases of a single planetary fluid that happens to exist in different states, different densities, different mobilities, but which is fundamentally continuous, fundamentally connected, fundamentally incapable of being divided, without doing violence to the truth of how the planet actually operates, how it maintains itself, how it persists across billions of years, not through stability, but through constant motion, constant exchange, constant transformation of matter, and energy between reservoirs that we name separately but which the planet experiences as one. There is another participant in this conversation between rock and water, one we have not yet properly acknowledged, and that is life itself, organisms ranging from microscopic bacteria to tiny plankton drifting in the sunlit surface waters, all of them extracting minerals from seawater, incorporating those minerals into their bodies, their shells, their skeletons, and then releasing those structures back to the ocean when they die, contributing to the sediment that accumulates on the seafloor, participating directly in the transformation of dissolved elements into solid structures, into rock in the making, showing us that the boundary between ocean and Earth is not purely physical, not exclusively a matter of temperature and pressure and chemical equilibrium, but also biological, also mediated by the metabolisms and life cycles of countless organisms that have no awareness of their role in planetary processes, but which collectively exert an influence comparable to any geological force, moving calcium and carbon and silicon from water to solid form, building structures that will eventually become limestone and chert and other sedimentary rocks, participating in the same slow transformation we have been following, just doing so through biological rather than purely chemical means, through mechanisms that involve respiration and growth and reproduction rather than simple precipitation. Though the end result is remarkably similar, mineral structures accumulating on the seafloor, adding to the boundary, thickening it, complicating it, making it even more difficult to say where ocean ends and rock begins. The organisms doing this work are mostly invisible to us without magnification. Single-celled creatures called foraminifera that build intricate chambers of calcium carbonate, coccolithophores that surround themselves with circular plates of calcite, radiolarians and diatoms that construct delicate skeletons of silica, each one a tiny artist working with minerals dissolved in seawater, extracting those minerals from solution against the concentration gradient, using energy from metabolism to power the process, building structures that serve them in life as protection or buoyancy or support, and that serve the planet in death as sediment, as the raw material for future rock, as limestone in the process of formation, not yet compressed into stone but already solid, already mineral, already crossing that boundary between what we call living and what we call geological, showing us that this distinction too is less absolute than we imagine, that life and geology are not separate domains, but overlapping ones, with organisms extracting materials from their environment and returning them in altered form, with geological processes providing the minerals that organisms use and incorporating the structures that organisms build, creating a feedback loop that has operated since life first appeared in the oceans, that has profoundly affected both the chemistry of seawater and the composition of seafloor sediment, that has made Earth different from what it would be without life, not just in terms of atmospheric oxygen or climate regulation, but in terms of the actual rocks that form the crust, the sedimentary layers that preserve the history of life, and also embody that history, that are literally made from the bodies and shells of organisms that lived and died over hundreds of millions of years. The scale of this biological contribution is staggering when you calculate it, with estimates suggesting that the majority of calcium carbonate sediment on the seafloor is biogenic, meaning it originated in the bodies of organisms rather than precipitating directly from seawater, which it can do, but does so much less readily without biological mediation, without organisms creating conditions favorable for carbonate precipitation, without the constant production of shells and tests and coccoliths that fall through the water column and accumulate on the bottom. Some areas of the seafloor are covered with ooze, consisting almost entirely of these microscopic shells, layers hundreds of meters thick, representing millions of years of continuous accumulation, continuous biological activity in the surface waters above, continuous participation of life in geological processes, blurring the distinction between ecology and geology, between what biology does and what chemistry does, showing us that at least some of what we call geology is actually biology. Operating at geological timescales, life processes integrated so completely into the planet's material cycles that they cannot be extracted or understood separately, that they are part of how Earth works, part of why our planet has the particular composition and structure it does. Part of the reason the boundary between ocean and rock is so complex, so gradual, so thoroughly interpenetrated with exchanges and transformations and transitions. But life participates in this boundary not only through calcification and shell building, but also through more direct interactions with rock, with microorganisms living in sediment, in the pore spaces between particles, in fractures within the oceanic crust, sometimes kilometers below the seafloor, surviving in conditions we once thought too extreme for life, too hot or too pressurized, or too lacking in obvious energy sources. And yet these organisms exist, metabolizing slowly, reproducing, rarely but persisting, maintaining populations that may be immense when summed across all the world's oceanic crust, contributing to chemical exchanges through their metabolism, affecting the oxidation state of minerals, the pH of pore water, the solubility of various elements, participating in rock-water interactions in ways we are only beginning to understand, in ways that challenge our assumptions about what life is and where it can exist, and what role it plays in planetary processes we thought were purely geological. These deep biosphere organisms, as they are called, may be using energy from rock-water reactions, from the hydrogen released during serpentinization, for instance, gaining energy not from sunlight or organic matter, but from the chemical potential stored in incompletely oxidized minerals, from the thermodynamic drive toward equilibrium that characterizes all rock-water interactions, inserting themselves into that process, accelerating some reactions and slowing others, creating conditions that differ from what purely abiotic chemistry would produce, showing us that even at these depths, even in these apparently lifeless rocks, biology is present, is active, is contributing to the boundary we are exploring, making it even more complex, even more thoroughly mediated, even less divisible into purely physical or purely chemical or purely biological components. And what becomes clear, as we consider life's participation in this boundary, is that the distinction between living and non-living, between organisms and their environment, between biology and geology, begins to seem as arbitrary as the distinction between ocean and rock, another convenience of classification that helps us organize our thinking, but that does not correspond to any fundamental separation in nature, to any clear line that divides one category from another, because life is made from the same elements as rock, is subject to the same physical laws as ocean, participates in the same chemical cycles as everything else, just does so in ways that involve temporary concentration of those elements into organized structures, temporary maintenance of conditions, far from equilibrium, temporary resistance to the entropy that will eventually disperse those structures and return those elements to the ocean and the rock and the atmosphere, but only temporary, only for the duration of life, after which the minerals return to sediment, the energy returns to heat, the organization returns to randomness, completing yet another cycle, yet another exchange, yet another demonstration that nothing on this planet is permanent, nothing is isolated, nothing is independent. Everything is participating in transformations that connect it to everything else, that make the whole planet one continuous system of exchanges and cycles and boundaries that are not divisions but connections, not walls but membranes, not endings but transitions, showing us perhaps that what we are exploring when we examine the boundary between ocean and earth is not really a particular place or a particular phenomenon, but a general principle, a fundamental aspect of how the planet operates, how it maintains itself, how it persists, not through permanence, but through constant transformation, constant exchange, constant dissolution of the boundaries we keep trying to impose on it. If we could shrink ourselves down, if we could observe these processes at the scale of individual molecules, we would see that what appears from a distance as solid rock is actually a dynamic assembly of atoms, held together by electromagnetic forces, by bonds that are strong but not unbreakable, by attractions that can be overcome when the right conditions are present, when water molecules approach and begin their patient work of dissolution, of separating ions from their crystal lattices, of carrying those ions away into solution where they become part of the ocean's chemical inventory, part of what makes seawater salty and rich in dissolved minerals, part of the mobile phase that contrasts with the solid phase of rock, but which is made from the same elements, just arranged differently, just existing in a different state, just participating in a different stage of the cycle, that moves materials between reservoirs, at rates that vary by orders of magnitude, but that all contribute to the same fundamental exchanges, the same slow homogenization of the planet's chemistry, the same tendency toward equilibrium that characterizes all thermodynamic systems given enough time and enough pathways for exchange. Water, at this molecular scale, is not the passive substance we might imagine, not simply a medium in which reactions occur, but an active participant, a molecule with a slight electric charge separation, with the oxygen atom carrying a partial negative charge and the hydrogen atoms carrying partial positive charges, creating what chemists call polarity, what we might think of as personality, a tendency to orient itself around ions, to surround them with shells of water molecules, to stabilize them in solution by compensating for the charge they lost or gained when they left their crystal lattice, making it energetically favorable for that ion to remain dissolved rather than returning to solid form, at least until conditions change, until concentration or temperature or pressure or the presence of other ions shifts the balance, and precipitation becomes favorable instead. But for now, at this moment, dissolution is winning. Water molecules are prying ions loose from mineral surfaces. Calcium atoms leaving calcite, magnesium leaving dolomite, sodium and chloride leaving salt deposits, silicon leaving quartz. Each departure facilitated by the attraction between water's partial charges and the ion's full charge, by the formation of a hydration shell that effectively replaces the crystal lattice as the ion's environment, that provides a new form of stability, a liquid one instead of a solid one, a mobile one instead of a fixed one, but stability nonetheless, showing us that dissolution is not destruction but transformation, not loss but redistribution, not the end of organization but a change in organizational principle. The crystal surface where this happens is itself complex, not perfectly smooth but interrupted by defects and irregularities. by places where atoms are less tightly bound, where dissolution happens more readily, where water can access bonds that are strained or incomplete, where the crystal structure is locally disrupted and therefore more reactive, creating preferential sites for dissolution that give the surface texture, that produce patterns of etching visible under magnification, showing us that even at the molecular scale, the process is not uniform but selective, not random, but guided by the specific geometry and chemistry of each mineral, by the particular arrangement of atoms in its structure, by the particular bonds holding those atoms in place, each type of mineral dissolving in its own characteristic way, at its own characteristic rate, some quickly and others slowly, some readily and others reluctantly, some producing simple ions in solution and others producing complex molecules, but all participating in the same fundamental process, all exchanging material with the water that surrounds them, all contributing atoms to the ocean's dissolved load, all thinning themselves imperceptibly with each ion that departs, all approaching a future when they will be completely dissolved, completely returned to solution, completely cycled back into the mobile phase from which they originally precipitated, though this future may be millions of years away, may be so distant that the mineral effectively persists indefinitely, effectively serves as permanent rock even while technically being temporary, technically being on its way toward dissolution, just moving so slowly in that direction that the distinction between permanent and temporary becomes meaningless, becomes a matter of timescale rather than of fundamental character. The ions, once in solution, do not remain stationary but move through the water, driven by concentration gradients, by random thermal motion, by the stirring of currents and the mixing of water masses, spreading gradually from areas of high concentration to areas of low concentration, diffusing through the ocean, becoming more evenly distributed, more thoroughly mixed, contributing to the ocean's overall chemistry, to its characteristic salinity, to the specific ratios of elements that define seawater as distinct from fresh water or from the water found in other environments, ratios that reflect the cumulative history of rock-water interaction, of evaporation and precipitation, of biological uptake and release, of all the processes that move elements between dissolved and solid phases, that contribute to or remove from the ocean's inventory, that maintain or disturb its chemical equilibrium, showing us that seawater is not a fixed composition, but a dynamic balance, not a static solution, but an actively maintained state, not a simple mixture, but a complex result of countless competing processes operating simultaneously at different rates, all of them contributing to what we measure when we analyze seawater, all of them represented in those ratios of sodium to chloride, of magnesium to calcium, of sulfate to bicarbonate, each ratio telling part of the story, each concentration reflecting particular pathways and particular rates, each element cycling through the ocean at its own characteristic residence time, some remaining dissolved for millions of years and others precipitating within centuries or decades, but all participating, all exchanging, all demonstrating through their presence in solution that the boundary between rock and water is not just porous but permeable, not just gradual but continuous, not just physical but chemical, extending down to the atomic level, down to the individual ions and molecules, down to the fundamental units of matter that compose both the solid and the liquid, both the rock and the ocean, both halves of the boundary we are exploring. And what this molecular view reveals, perhaps more clearly than any larger scale observation, is that the boundary is not a thing but a process, not a location, but an activity, not a surface, but an interface where exchange is constant, where atoms move in both directions, though typically at different rates, where what matters is not the instantaneous state, but the long-term balance between dissolution and precipitation, between rock becoming water and water becoming rock, between solid, releasing ions and solution-depositing minerals, all of it happening simultaneously, all of it contributing to the gradual evolution of both the seafloor and the ocean, all of it demonstrating that separation is provisional, that categories are temporary, that what we call distinct at one moment may be continuous at another, that the atoms currently bound in a crystal may soon be dissolved in seawater, and the atoms currently dissolved may soon precipitate as new minerals, and that neither state is more fundamental than the other. Neither one represents the true nature of the material, only its current configuration, its present participation in ongoing cycles, its momentary role in processes that will continue long after this particular atom has moved on, has cycled through other phases, has participated in other transformations, has contributed to other boundaries, other exchanges, other demonstrations of the planet's fundamental continuity. The ocean we see from shore, the one we swim in or sail across or watch from the beach, does not reveal its connection to the processes we have been following, does not show us the seafloor kilometers below, or the circulation through oceanic crust, or the slow dissolution of minerals, or the cycling of water through the mantle. And yet all of these hidden processes shape what we observe at the surface, determine the ocean's chemistry and temperature distribution, and even its color. The particular shade of blue or green or gray that we associate with seawater, that we recognize immediately, even though we rarely think about what causes it. What makes ocean water look the way it does? Why it differs from lake water or river water, or the water that comes from our taps? Differences that seem superficial but which actually reflect profound connections to everything we have been discussing. To the rock-water interactions happening in darkness and pressure. To the exchanges occurring across boundaries we cannot see, to the integration of surface and interior that makes Earth the particular planet it is, rather than some other drier or wetter or chemically different version of a rocky world. The salinity of seawater, for instance, that characteristic saltiness that makes it undrinkable despite its abundance, reflects the cumulative result of billions of years of rock-water interaction, of minerals dissolved from the seafloor and from continental rocks, of elements released through weathering and volcanism, of chemical exchanges at every interface between solid and liquid, all of it contributing to the specific mixture of dissolved ions we measure when we analyze seawater, with sodium and chloride dominating, but with magnesium, calcium, potassium, sulfate, bicarbonate, and dozens of other elements present in smaller but significant concentrations, each one representing particular sources and particular pathways, each one cycling through the ocean at its own rate. Some added continuously through river input or hydrothermal circulation, and removed continuously through biological uptake or mineral precipitation, maintaining approximate balance over long timescales, but varying in detail, responding to changes in volcanic activity or in the rate of seafloor spreading, or in climate patterns that affect weathering rates on land, showing us that even this basic property of seawater, its salt content, its chemical signature, is dynamic rather than static, connected to geological processes rather than isolated from them, shaped by the boundary between ocean and earth, even though that boundary is far from shore, far below the surface, far from any place we typically look when we try to understand the ocean. The ocean's temperature distribution, too, reflects connections to the seafloor and to the heat flow from Earth's interior, with cold water sinking at high latitudes and forming deep currents that spread across the ocean basins, filling them from the bottom up with water that originated at the surface, but which now moves slowly through darkness, taking centuries or millennia to complete its journey, gradually warming through contact with the seafloor, through the diffuse heat flux that escapes, through sediment and rock, through the more concentrated heat released at hydrothermal vents, all of it contributing to the ocean's overall heat budget, to the balance between energy received from the sun and energy lost to space, to the regulation of climate that the ocean provides through its enormous heat capacity and its ability to move heat from equator to poles through both surface and deep circulation, creating the relatively moderate temperature variations that characterize Earth's climate, preventing the extremes that would exist without this thermal buffering, without this connection between surface and interior, without the ocean serving as intermediary between the heat generated in Earth's core and mantle and the cold of space, absorbing and redistributing that heat, making life possible in more places and under more conditions than would otherwise be the case. Even the ocean's biological productivity, The abundance of life in certain regions and its relative scarcity in others connects to these hidden processes, to the circulation that brings nutrient-rich deep water back to the surface at upwelling zones, water that has been enriched with phosphorus and nitrogen and iron and other elements through contact with sediment, through decomposition of organic matter that sank from the surface, through input from hydrothermal systems that release these elements from rock, making them available to phytoplankton when the water returns to the sunlit zone, enabling the photosynthesis that forms the base of oceanic food webs, the primary production that supports all the fish and whales and seabirds and other conspicuous life we associate with the ocean. All of it ultimately dependent on nutrients whose availability is controlled by processes happening in darkness and depth, by the slow cycling of elements between rock and water and organisms and sediment, by exchanges occurring across boundaries we cannot observe directly, but whose effects ripple through the entire ecosystem, shaping where life can thrive and where it struggles, where fisheries are productive and where they are not, where coral reefs build and where they cannot sustain themselves, all connected to the chemistry and circulation patterns established through rock-water interactions, through the boundary we have been following, through the integration of solid and liquid. Earth. Standing at the shore, watching waves approach and retreat, feeling the spray on your face, tasting the salt on your lips, you are participating in this system, sampling its output, experiencing its surface expression, touching the edge of something that extends far beyond what you can see, that includes the seafloor beneath and the mantle below, and the water cycling through rock and the minerals dissolving and precipitating, and the organisms building shells and the sediment accumulating, and all the other processes we have been exploring, all of them present in this water touching your skin, all of them represented in its temperature and salinity and chemistry, all of them contributing to the particular character of this ocean on this planet at this moment, making it different from what it was 1,000,000 years ago, and different from what it will be 1,000,000 years hence, always changing but always recognizably itself, always the same ocean, and always a different ocean, always connected to the rock beneath it, and always distinct from that rock, always participating in exchanges, and always maintaining its identity, showing us through its very existence that boundaries need not be barriers, that connection and distinction can coexist, that the ocean can be both separate from and continuous with the solid earth, both its own domain and part of a larger system, both an independent feature and an integrated component, depending on how we choose to look at it, what scale we examine, what questions we ask, what aspects we emphasize, revealing perhaps that our perception of separation tells us more about our cognitive categories than about the planet's actual organization, that we impose these divisions because they help us think and communicate, because we need names for things and boundaries between concepts, but that the planet itself operates according to different logic, according to principles that prioritize continuity over separation, exchange over isolation, gradual transformation over permanent identity, asking nothing of us except that we notice, that we slow down enough to see what has always been there, waiting patiently for our attention to arrive. We are ourselves boundaries, interfaces between inner and outer, collections of membranes and surfaces where exchange occurs, where what is inside meets what is outside and the distinction becomes negotiable, provisional, maintained only through constant effort, constant metabolism, constant work against the tendency toward equilibrium that would eliminate the difference, that would allow the inside to mix with the outside and return us to the undifferentiated state from which we emerged, the state that awaits us eventually, that we resist temporarily through the mechanisms of life, but which we cannot resist permanently, because we too are participating in exchanges, in cycles, in the same fundamental processes that characterize the boundary between ocean and earth, just operating at different scales, at different rates, using different materials, but following the same basic principles, the same thermodynamics, the same inexorable movement towards states of lower energy and higher entropy that everything in the universe participates in, everything without exception, including us, including our bodies that are mostly water, that contain the same elements as rock and ocean, that cycle those elements through our metabolism and return them to the environment when we die, completing our own small contribution to planetary cycling, our brief participation in the movement of matter through different forms and different states and different levels of organization. Your skin is a boundary, permeable to some things and impermeable to others, selectively allowing water to pass through as sweat or preventing it from passing in when you swim, maintaining a chemical composition inside your body that differs dramatically from the chemical composition outside, concentrating some elements like potassium and excluding others like sodium, creating gradients that enable nerve signals and muscle contractions and all the other electrical phenomena that make thought and movement possible, that make you a living organism rather than an inert collection of chemicals. But this boundary is not absolute, not perfect, not impermeable to everything, because you breathe and therefore exchange gases with the atmosphere, because you eat and therefore incorporate material from outside your body, because you excrete and therefore return material to the outside, because you are constantly exchanging, constantly cycling, constantly maintaining yourself through flow, rather than through isolation, through participation in the larger system, rather than through separation from it, showing that you too are continuous with your environment, even while being distinct from it, that you too represent a temporary concentration of organization that will eventually disperse, eventually return to simpler states, eventually contribute your constituent atoms to other structures, other organisms, other phases of planetary cycling. The oxygen you breathe was produced by photosynthesis, mostly in the ocean, by phytoplankton using energy from sunlight to split water molecules and release oxygen as a byproduct. Oxygen that rises into the atmosphere and eventually finds its way into your lungs, into your bloodstream, into your cells, where it participates in the reactions that release energy from food, that power your metabolism, that keep you alive and conscious and capable of thinking about boundaries and oceans, and the slow processes that shape planets, and when you exhale, you return carbon dioxide that plants and phytoplankton will use to build new organic molecules, to grow, to participate in their own metabolism, completing a cycle that connects you directly to the ocean's primary producers, to the biological processes happening in sunlit surface waters, to the broader carbon cycle that involves atmosphere and ocean and rock and life, that operates on timescales ranging from seconds in your respiration to millions of years in the formation and weathering of carbonate rocks, all of it connected, all of it cycling, all of it demonstrating that boundaries are not barriers but membranes, not walls but interfaces, not places where things stop but places where things pass through, where exchange occurs, where the inside and outside negotiate their relationship through constant traffic in both directions. The water you drink may have fallen as rain last week, or may have been underground for centuries, or may have cycled through the ocean and the atmosphere many times over millions of years. Impossible to know its specific history, but certain of its general participation in the water cycle we discussed earlier. The cycle that includes surface exchange and deep exchange, rapid loops and slow loops, pathways through the atmosphere and pathways through rock, all of it contributing to the water that exists in any particular location at any particular time, including the water in your body, the water that makes up more than half your mass, that fills your cells and surrounds them, that serves as the medium for all your biochemistry, that makes you literally more water than anything else, more ocean than earth in composition if not in form, carrying within your body the same chemical signature as seawater, the same sodium and potassium and chloride and phosphate, just in different ratios, just concentrated differently, just participating in different immediate cycles, while remaining part of the same ultimate cycling, the same planetary movement of matter that includes everything, that excludes nothing, that makes distinctions between ocean and rock and organism ultimately arbitrary, ultimately conventional, ultimately useful for some purposes, but misleading for others, particularly when we want to understand connection rather than separation, integration rather than isolation, continuity rather than division. And perhaps this is why contemplating the boundary between ocean and earth brings a certain calm, a certain perspective, because it reminds us that we are not separate from these processes, not observers standing outside the system we study, but participants within it, not fundamentally different from the rock and water we have been discussing, but fundamentally similar, made of the same material, subject to the same laws, participating in the same exchanges, just happening to be organized in a way that enables consciousness, that creates the capacity for reflection, that allows matter to become aware of itself and consider its own nature, its own impermanence, its own participation in transformations that began long before we appeared and that will continue long after we are gone, that connect us to everything that came before and everything that will come after, that make us not isolated individuals, but temporary expressions of patterns that the universe has been exploring for billions of years, variations on themes that include stars and planets and oceans and rock and life, all of them different in detail but similar in principle, all of them participating in exchanges, all of them existing at boundaries, all of them maintained through flow rather than through stasis, through constant transformation rather than through permanent identity, showing us that perhaps the deepest truth about existence is not permanence but change, not separation but connection, not independence but interdependence, not boundaries that divide but boundaries that unite, that enable relationship, that make exchange possible, that create the conditions for complexity and diversity, and the emergence of properties that cannot exist in isolation, that require interaction, that demand participation in something larger than any individual component, something that includes ocean and earth and life and consciousness, something that we are part of whether we recognize it or not, something that continues its patient work regardless of our attention or understanding, something that asks nothing of us except perhaps that we occasionally pause and notice, that we slow down enough to feel our participation, to recognize our connection, to understand that we too are boundaries where different aspects of the universe meet and exchange and create something neither one could create alone. What we have discovered by following this boundary, by examining how ocean and earth meet and merge and become indistinguishable from each other across sufficient time and depth, is perhaps not limited to this particular interface, not unique to the relationship between water and rock, but rather exemplifies something more general about boundaries themselves, about the nature of transitions in physical systems, about how the universe actually organizes itself when left to operate according to its own principles rather than according to our categorical convenience, our need for clear divisions, our preference for distinct objects with definite edges rather than gradual transitions with ambiguous extents. And what we find, when we look carefully at almost any boundary we might choose to examine, is that the pattern repeats, that what appeared sharp from a distance reveals itself as gradual up close, that what seemed like a clear division turns out to be a zone of interaction, a region, where both sides of the supposed boundary coexist and interpenetrate and exchange properties, creating not two separate things, with a line between them, but one continuous system with regions of different character, different density, different phase, but all connected, all participating in exchanges, all influencing each other across the supposed divide. The atmosphere does not end sharply at some altitude, but fades gradually into space, with molecules becoming rarer and rarer as you ascend, with no clear point where you can say, here is where atmosphere stops and space begins, only a gradual transition that extends across hundreds of kilometers, with the thermosphere and exosphere representing not the end of Earth's atmosphere, but its gradual merging with the interplanetary medium, its slow fade into the near vacuum between planets, showing us that even this boundary, even this division between planet and space that seems so fundamental, is actually gradual, actually fuzzy, actually impossible to locate, precisely because it exists not as a surface, but as a gradient, not as a boundary in the sense of a barrier, but as a boundary in the sense of a zone where properties change continuously from one set of values to another. The Earth's core does not end at a sharp interface with the mantle, but transitions through a complex boundary layer where temperature and pressure and composition all vary continuously, where convection patterns in the liquid outer core interact with conduction patterns in the solid lower mantle, creating a region hundreds of kilometers thick where neither core nor mantle fully describes the material, where both characterizations are partially correct and partially misleading, where the reality is more complex than either term suggests, showing us again that boundaries are not where things stop, but where things interact, not divisions but connections, not barriers but interfaces that enable exchange. Even in our daily experience, even in the most familiar phenomena, this pattern holds, with day not becoming night at a single moment, but transitioning through twilight, through that gradual dimming that takes half an hour or more depending on latitude and season, during which time the sun is neither fully above the horizon nor fully below it, but somewhere in between, illuminating the upper atmosphere while leaving the surface in shadow, creating those long, gradual changes in light and color that we find beautiful precisely because they are gradual, because they give us time to adjust, because they do not force us to choose between day and night, but allow us to experience the transition, to inhabit the boundary, to exist for a while in that liminal space where both conditions are partially true, where the categories we use to organize time reveal themselves as approximate, as conventional, as useful, but not ultimate, not corresponding to any sharp change in the world itself, but only to convenient divisions we have imposed on continuous variation, on the smooth rotation of a planet that recognizes no distinction between day and night, only between the side currently facing the sun and the side currently facing away, with a twilight zone connecting them, always moving, always transitioning, always in between. Perhaps boundaries are more common than the things they supposedly separate. Perhaps transitions are more fundamental than states. Perhaps the gradients and interfaces and zones of interaction that connect different regions, or different phases, or different categories are actually where most of the interesting phenomena occur, where most of the complexity emerges, where properties exist that cannot be found in either of the supposedly distinct things on either side of the boundary, but only in their interaction, in their exchange, in the particular combination of characteristics that exists nowhere else, creating unique environments, unique conditions, unique opportunities for processes and structures that require exactly this combination of properties, exactly this balance of influences, exactly this location at the interface where different forces meet and negotiate and create something neither could create alone. Life itself may have emerged at such a boundary, at interfaces between rock and water, between reduced and oxidized chemicals, between energy-rich and energy-poor environments, taking advantage of the gradients that exist at these interfaces, using the flow of material and energy from one side to the other, to power metabolism, to maintain organization far from equilibrium, to create the complex chemistry that eventually became biology, became consciousness, became us standing here contemplating boundaries and wondering what they tell us about the nature of existence. The ocean-Earth boundary, then, is not an exception, but an example, not a special case, but a typical one, not unique in its gradualness, but representative of how boundaries actually work when you examine them carefully, when you look beyond the convenient abstractions we use in everyday speech and everyday thought, when you pay attention to what is actually there rather than what we assume must be there, and what is actually there, consistently, repeatedly, in case after case, is not sharpness, but gradation, not division, but connection, not separation, but interpenetration, not isolated systems, but integrated ones, not independence, but interdependence, not boundaries that divide the world into separate pieces, but boundaries that weave the world together into one continuous whole, into one integrated system where everything affects everything else eventually, where nothing is truly isolated, where the distinctions we draw are provisional and pragmatic rather than fundamental and absolute, useful for certain purposes, but misleading for others, helping us navigate and communicate, but potentially preventing us from seeing deeper patterns, deeper connections, deeper truths about how the universe actually operates, how matter and energy actually flow and exchange and organize themselves into the structures and systems we observe, suggesting that perhaps the deepest understanding comes not from perfecting our categories, but from recognizing their limitations, not from sharpening our boundaries, but from acknowledging their gradualness, not from separating things more precisely, but from appreciating their connections more fully, from learning to see the world not as a collection of objects, but as a web of processes, not as a set of things, but as a set of relationships, not as nouns, but as verbs, not as states, but as transformations, not as permanence, but as constant change maintained through constant exchange, through constant flow, through constant participation in cycles and interactions that connect every part to every other part across time and space, and through all the boundaries we imagine divide them. Perhaps what we have been doing all along, throughout this long descent into darkness and depth, throughout this patient examination of how ocean and earth meet and merge, is learning not to understand, but to accept, not to solve a mystery, but to inhabit it more comfortably, to recognize that some questions do not seek answers, but only deeper questions, that some boundaries exist not to be crossed or eliminated, but simply to be acknowledged, to be appreciated for what they enable, rather than what they prevent, for the exchanges they facilitate, rather than the separations they mark, and that the ocean-earth boundary, this zone where solid and liquid have been conversing for billions of years without reaching any conclusion, without arriving at any final state, represents something essential about the planet's character, about its refusal to be static, about its commitment to transformation over permanence, to process over product, to becoming over being, asking nothing of us except that we notice this patience, this unhurried certainty with which the planet conducts its affairs, this willingness to let things take as long as they need to take, to let reactions proceed at their own pace, to let equilibrium approach slowly, asymptotically, never quite arriving, but always moving in that direction, always adjusting, always fine-tuning, always participating in the slow work that geological time makes possible. The darkness we began in, that sense of arriving somewhere undefined, somewhere between categories, somewhere that resisted easy description, has not been replaced by light or by clarity, but has instead been filled with detail, with process, with the specific mechanisms by which rock and water conduct their conversation. And yet the mystery remains. The fundamental question of where one becomes the other still has no sharp answer, still resolves itself into gradients and zones and transitions that extend further than we initially imagined, that include more processes than we first suspected, that reveal complexity where we might have expected simplicity, showing us not that the boundary is more complicated than we thought, but that our thinking about boundaries was simpler than the world actually is, that our categories were rougher than reality, that the planet has been operating all along, according to principles we are only beginning to recognize, principles that prioritize connection over division, that maintain unity through diversity, that create stability through change, that preserve the whole by constantly transforming the parts, cycling everything, exchanging everything, keeping nothing in permanent isolation, nothing in permanent form, nothing exempt from the slow redistribution that time enables. And so, we find ourselves back where we started, in a sense, standing at the edge of something vast and mostly hidden, something that extends far beyond what we can see or touch or measure directly, something that continues its work regardless of our understanding, regardless of our attention, regardless of whether anyone is watching or wondering or trying to trace the pathways by which seawater becomes rock and rock becomes seawater, and both participate in cycles that encompass the entire planet, that connects surface to interior, that integrate every domain and every process into one continuous system, one persistent conversation that has no beginning. We can identify and no ending we can foresee. Just this ongoing exchange, this patient negotiation, this gradual approach towards states that will never quite be reached because the conditions keep changing, because the planet keeps cooling, because the sun keeps shining, because life keeps metabolizing, because everything is always moving, always transforming, always becoming something slightly different from what it was while remaining recognizably itself, maintaining identity through change rather than through permanence, showing us that perhaps this is the deeper pattern, the more fundamental truth, that everything exists at boundaries, that everything is a transition between states, that nothing is ever finished or final or separate, only temporarily organized, temporarily concentrated, temporarily distinct before, returning to the flow, before rejoining the cycles, before dissolving back into the exchanges that characterize all matter and all energy in this universe, this vast process that we participate in, that we are made of, that continues through us and around us and will continue after us, asking nothing, offering everything, present always in the silent depths where earth and oceans slowly become one. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.